If you need a copy, I can send it to you.
Okay.
Okay, that's it's good to have some copy here. All right.
Hmm.
Yes, continue. So what is direction of the current? It's downward.
Direction of the
Yeah.
current. Yes. Yeah.
So you can put actually you can put an arrow here. Can we? You can put an arrow here. So you can use this arrow to indicate the direction of current in this case. It's current direction. So the vector. Okay. And so
Yeah.
from this diagram, so can you convince that the angle between these two angles are 90 degrees?
Yes.
Yes, that's right. That's right.
Yeah.
Okay. Now, have you studied cross product in vector? Vector.
Yes.
Yeah.
Yeah.
So how to define? In this case, we have two vectors. Okay, we got the magnetic field. We got the electric current. Okay. In this case, it's 90 degrees. But in general, we just call this angle is theta. Okay.
Theta. Right. Yeah.
Can you use right hand to determine the direction of the force in this case?
Right.
So this angle. So can you see this is B
towards the? Oh yeah.
Yeah, upward, downward, upward.
We'll be going upwards.
Good. Yeah, that's what we call the right hand law. Can we use this color? Which color to use force? Can we say? Can we got all color? Can we use green? Can we use green?
Yeah. Okay. Green.
So this is the CNC. So there are two ways. Okay. It will if you have you studied the vector geometry. You use vector to determine the plane. Have you studied in Math C? Have you studied that?
Yeah.
Yes, that's exactly the same. So you see, if this is a cross product, the direction of the product must be perpendicular to the plane where the two vector 9. Okay, okay. So if the charge, if the current, so that would be okay. I write down here. So that in this case, that you have two choice, this way or this way. Okay. Because that is force. So they got in force. Okay. Yeah. Do you still find it challenging? That's all. That's all about ampere force.
Right. Yeah. Okay. I think there was just one question in the test that I got wrong, so I thought I needed to practice that style of questions and all. Yeah. But
this force is also related to another force. Normally, if you go to university, called Lorentz force. Lorentz force. And in your textbook, you wouldn't call it Lorentz force, but if I write it down, you would know it. So Lorentz force is a F or equal to Q, right? Velocity multiply cross product B. Do you remember this formula?
Yes. Yeah.
So if you have charge, can I say a positive charge in the space, right? If the charge is moved at a certain velocity, so if the charge is moved at a certain velocity, okay, say this way, okay, and if the current, if the magnetic field is inward, we just consider the similar scenario. Or probably I will put it downward. I will put it downward because we can compare with our scenario here. So basically. So this is a charge park move downward, okay, and in the space they also have uniform magnetic field. So can we into the page? Okay, it's into the page.
Okay, into the page.
Into the page. So it's got to be here. Now in this case, the moving charge will experience the force. Have you studied that? So if this is velocity, and this is magnetic field. So the moving charge will experience the force, which can be written as this form. Of course, in the special, if you just consider the magnitude, the F, as we did before, F can be written as a QVB sine theta. Same. Okay. This theta is a direction between the velocity and the magnetic field. So if the theta equal to 90 degrees, then this is the formula we will often use. QVB. Do you know this formula? You better review these two formulas together. So one is ampere force, special case. This is called the Lorentz force in the special case. Have you studied this formula?
Yes, we have. Yeah.
Yeah. So if I just let me just draw the diagram. So similarly, this in general. So in this case, if this is velocity, I just put this diagram side by side so you can compare. And the origin color will represent the the magnetic field. Okay. So what would be the direction of the force, Lorentz force in this case?
Lorentz force.
Downward, upward.
Wait, B.
Yeah.
Still upward, right?
Yep. It's up. That's right. It's up. It's upward. So you see, these two forces are related. Have you ever thought of that?
Are related.
Yeah, these two forces are related. Did you know that?
That way.
Can we call this a velocity? This is a magnetic field. That would be the Lorentz force. Okay, I put some data here. Can you say A for Lorentz force here?
Yeah.
So A for ampere force. Okay, this is for ampere force. Can you see the similarity? What's going on here?
So yeah, I see.
By the way, I give you a chance. Can you label the force, the two force in the two scenario? Can we label the force?
Label the force.
Can you use arrow? Can you pick up the arrow to label the force of the bar acting on the bar and the force acting on this moving charge? All right. Can you choose say the green colored arrow to indicate where is it? What is the direction of this force?
Okay, so in this one. Oh wait. The force would be going this way.
Yeah, let me try.
Like that.
Force. Yeah, yes, you're right. Yeah, you're right. Yeah, how about this scenario? How about this one?
And this one.
Yeah.
Wait. Would be going the same way like this, right?
Yep, that's right.
Yeah. Okay.
Is that strange? What's going on? What are these two forces are independent force, or they actually belong to the same type of force? Or in other words, can you describe the ampere force in terms of the Lorentz force? Have you ever asked this question at school?
No, I haven't.
No,
I haven't thought of it that way yet.
Okay. So there are so many formulas in physics, right? But some of them are related, so you don't have to consider this as independent formula.
Oh, okay. Yeah, so they're related, the two.
They are related.
The forces are right.
Yeah. Do you want to prove that?
Yeah. Okay. We'll try.
Okay.
Yeah.
Let's prove that. Okay.
Yeah.
Okay.
Okay.
Now, if you just so let's give you some extra. So because that will help you to understand the physics. Okay. Because this bar indicated the current. Okay. Now can we just clear up this part because we want to draw some pictures here. So now just to clean up this little bit. Okay, we know the current is downward. Okay, we know current downward. That instead, can we just consider that? Let's just draw this diagram. Can we just consider this arbitrary section? Can you see? I use a different color. So can we just consider this arbitrary section? Can we call this delta x? Okay, this length is delta x. Can we call it delta x? Okay.
Okay. Yeah.
And the cross section, can we call this cross section A? A is a cross section. Can we just consider just cylinder? Okay.
Okay. Yeah.
So therefore, they are. If you just see this one, they must have some electron or positive. In this case, we just consider the charge. Okay. Positively charged inside. Okay. Positively charged. Can you use the white? Can you see the charge? And of course, the charge is everywhere. Is actually moving. Okay. If this is positive, okay, if this is positive, they must be moving at a certain velocity, okay? Do you agree?
Yeah,
the velocity downward, can you see? Similar to this time, okay?
Right, yeah.
So that you can see, you almost can see. So basically in this time, I use the arrow to represent the velocity, okay? So all these positive charge are moving with the same velocity. Okay, of course, this ideal case, you can call it effective velocity, right? So all the electrons move downward with velocity. So of course, according to Lorentz law, each of these positive charge, so these are positive charge, so they are positive charge, or you can call it what you call in chemistry, what called cation?
Cations.
Cation, okay, but actually it's wrong, but we use wrong. Cation, cation, okay, positive charge, cation, right?
Cations, yeah.
Cation. So each of them will experience the force as you have obtained, do you agree? We just consider each of them. So the force will be towards this direction. You see that?
Yeah.
So in other words, each electron, apart from their downward motion, they will bend the bar toward the right-hand side.
Right.
Do you agree?
And that's what creates the force, yeah.
This is just one electron. Think about this is just one charge, okay? Now, how many charges make this contribution? How many charges?
Many, lots and lots.
Lot of them. So basically, by definition, if we just count this, how many charge in this small cylinder here, can we just consider this a very small cylinder? Can we say this is a? Can we just consider this very small? Oh, I'm trying to draw this diagram nicely so you can use repeatedly. So we just count how many charge here, okay? If they have a charge, can we say? Can we use a number? Can we say this charge is the number, the total number in this small cylinder is n, okay? So therefore, the total charge, so this, can we say n multiply, how to say, can we just call it delta Q? We don't want to know the number. Can use delta Q?
Okay, yeah.
It's delta Q in this small cylinder, okay? In terms of the, how to say, by definition, they are moving. They are moving downward. Okay.
They're moving down.
By definition, delta Q over delta T will equal to what?
Delta Q. Was that?
The charge passing through the cross area.
Oh, current.
It's current. Okay.
Yeah.
Okay, that's one equation. This is by definition. Okay.
Right. Yeah.
Another thing, you can also say the charge in the volume. The number of charge in the volume can be written as, how to say, can we use this because they are moving at the velocity v. So delta x will equal to delta t multiplied velocity. You agree?
X equal to t. Yeah. Okay.
Okay. So what can we say now? So basically, we just move to the how to solve that. So basically, can we just calculate the individual force? Can we just calculate this force inside? Can we just call this force is delta F inside all the contribution made? Okay.
Okay.
So these forces are because identical, so we can simply use this. We can replace this Q by delta Q. Okay.
Delta Q. Yeah.
Okay. And put the velocity of their common velocity because we just assume the particle move at the same velocity. Okay.
Yeah.
And also the magnetic field is uniform, then that will be B, okay? That is part of the force. Do you agree? That is a part of force.
Yeah, yeah.
Will be experienced, right? In other words, now we're trying to explain amper force in terms of Lorentz force.
Right, okay.
Okay, so what can we do next? So what can we do next? Next one, we can actually how to divide. By the way, how to divide velocity?
Divide velocity.
Yeah. You have to remember what is the definition of velocity, which here is constant.
Velocity. Was it distance?
Not the distance. Displacement over what?
Over time.
Over change in time. Okay.
Change in time.
All right. Yeah. These are all the formulas we need. And we have to eventually edit them
get
up.
The ampere force.
Up,
right.
Okay. So basically, if you just in this case, this one just give you a small amount of force. Okay, can we write this one? So delta F will equal to delta Q multiply delta x and delta t and multiply with magnetic field. Do you agree?
Yeah.
Now, by definition, this term equal to velocity. Okay, that's velocity. Now, here we are not interested in velocity. Can we just do some trick? Can we just shift this delta q under delta t under delta q and make this delta x there? Can we do that?
Oh, yeah.
What do we get? What do you get? Tell me what do we get?
I.
Yes, that's I. Can you
delta
see?
X.
Can you see we see I here now? Can you see? We can see I and B, but in this case, we didn't say L yet, not yet. This I, B multiplied delta X, okay?
Yeah.
Now, next time, have you studied Kankenesis? Have you studied Kankenesis?
Calculus, yes.
So you have studied Kankenesis. So basically, this can be written as a dF equal to IB. IB are constant. And the dx, okay?
V dx, yeah.
So what can we do? We can just do the integration. From 0 to L. This L is distance, okay? Can you follow me?
Okay.
So that will give the total force. As it gives the total force, can we call it ampere force? Of course, we don't call it now. We don't call it now, but it is ampere force now. I just call it force.
Right,
okay?
yeah.
That force will equal to integral. Can you call it the constant outside?
V.
This is a dx. X from 0 to L.
To L.
What is the result?
It's equal to L.
No, IBL, can you see?
Oh, IBL, yeah.
Okay. So we can safely say this is nothing but the ampere force, can you see?
Yeah.
You see that?
I see.
So if you in your spare time during the holiday, if you can play this derivation, that will help you to understand the physics.
Right. Okay.
Okay. This formula. So this formula is identical to this guy. Can you see?
Right. So you derive it from the Lorentz force.
That's right.
Yeah.
They are not independent. They are not separate. Just the number are different. So you can consider many charge experience force, and all charge will bend the right hand side. Okay, they will bend the right hand side. So that is why you get this
force. Yeah.
Okay. Next question.
I did have a question. Remember that test we were doing last time?
Yeah.
I had one question about this. About question 5.
You can write or draw anything. You can write. You can draw anything on this board.
I'll try. I don't think I can write it because it's a pretty long question.
You can email to me. I have another computer. I can display your email immediately.
I emailed it to you last lesson. It's question 5 of the second paper. Yeah.
Last lesson. Let's check my email. Last lesson received. Do you remember the date? Which date? Last lesson
was 11th, I think.
11, yeah, I got 11. Part of paper 2, is it at part of
paper 2? Yes, paper 2.
Paper 2. Okay, I got paper 1. Okay, I will open this paper. Yes, that's public use, right? That is one. Okay.
Yes, that one. I wasn't sure how to do question 5.
Question 5. Let's go to question 5. Now, question 5. Let's go to A, B. Question 2. Let's be last one. Question 5. Yeah, 6 mark. Yeah. Okay.
Yes.
Electrical energy EV. Okay. The first question: are you familiar with convert EV into say Joule? How to convert this? Have you considered using this? How EV into the Joule? How to convert into the Joule?
Let me see. EV into Joule. There's like a 1 EV is equal to 1.6 times 10 to the negative.
Why?
19 joules.
Why?
Why?
Yeah, right. You memorize that. You check that.
Yeah.
But what's the reason?
Yeah, I checked that. Is it because it's too small to measure? It's an easier way to measure the energy.
How do you get this magical number? How did you get this magical number? What does this number mean?
Not sure.
You're not sure? Oh, well, that's
Yeah.
the first question. You didn't answer. So basically,
Right, yeah.
1 joule. So the joule is a unit of the energy. Do you agree? So
Yeah.
these are notation. When you at the school, do you know this notation? This is called the dimension. This is called the dimension of the physical property. In other words, when you see this square bracket, it means we are interested in their unit. Okay. In this case, these are all equal to joule. So the energy and also the heat are also. I can put a Q here. I think that at this stage, I will use this general notation. Okay. What does the equation mean? That means that the dimension or the unit of these 3 physical quantity are the same. They all called the joule. Okay, work done. And do you remember the formula that work done in the electrical field with potential equal to Q times potential difference? Do you know this formula?
No, I don't remember that one.
Ah, that's very basic formula.
Oh, okay.
Oh no, hurry up. You don't forget about relativity and the standard model. This is very important. Okay.
Right.
It's
okay.
important. Because this is work done by the charges. For example, I drew the diagram. Probably you will use. I'm not sure. I just glance at your diagram. You're probably going to use this diagram here. Okay, I just drew here. This is capacitor. Okay, it's just two parallel plate, metal plate. Okay.
Right. Yeah.
Okay. In this case, if you just this is often used in the test. Okay. So if you just connect the battery, so this is positive side, and this is negative side. Okay. So the positive because this is a gap there, so the electric charge cannot move. The only thing you can do this is electron just once you switch, you put a switch here. Once you switch on, the electron will jump to these 2 sides. So the positive charge will stand here. Okay. Negative charge will stay this side. Have you seen this diagram before? Okay. As a result, they create the magnetic, electrical field. This is not magnetic now, it's electrical field.
Electrical field, yeah.
Electric field is downward, can you see? The electric field, it's uniform. It's uniform, okay? Okay. So in other words, if you put this is the electrical field, I will just give a summary here. That's why I recorded this session, because you can listen or watch it again and again. So this is this is electrical field, okay? Strings. And if you put the electric charge here, positive electric charge, can you find the force? Can you tell me the force, the positive charge in this uniform electric field? What is the direction of the force? What is the direction of the force?
The charge going down.
Can you say use arrow?
The pass charge, so it'll go towards the negative, right?
Yes, downward. Okay.
Yeah.
Can we just use our notation? I use a green color. So the force will be downward. Okay.
Yeah.
This is applied for positive charge. So which formula did you use? Which form? If you do want to calculate this force, what is the formula? Do you remember? So what is a
F is equal to EQ?
Yes, that's right.
Yeah.
Or QE. Do you agree?
QE, yeah.
Okay.
QE.
That's the first basic equation when you're dealing with electromagnetism. That is a force, okay? We don't use so when you calculate the force, we don't have to use Coulomb law, okay? If we can determine, the electric field is given, we don't have to use the Coulomb law. So this is the formula we use, okay? Another formula relevant. So if this voltage is called the voltage. What is voltage? Voltage is actually the difference between the 2 potential over here. Can you see? Can we see the V is positive and it is V negative? So the voltage, the so-called VO. When you study electricity, voltage actually means the potential difference between the positive charge and the negative charge side. Okay.
Right. Okay.
So voltage is a difference. It's not the absolute. voltage is a relative number, okay?
Right, okay.
So the voltage here, because we use a conductor, so therefore you can argue that, so the voltage here is also positive, and the voltage here is also negative. Do you understand? Because
voltage here, oh yes.
Yeah, because this is metal, there's no resistance. So therefore, the voltage at this point on this plate, it should be equal to this point next to the battery positive side. Okay.
Right.
In other words, the voltage across the two side of battery were equal to the voltage across here. Do you agree?
Oh,
now,
yeah.
if you call this distance between the two gap is a d, okay, then there's a formula that E can be written as this. Also, if you check your formula sheet, that be equal to voltage. So that I have written down here the voltage multiplied divided by d. Can you check your formula sheet? Can you see these two formula?
V. It should be in electromagnetism.
Yes.
We have V is equal to change in U over Q. Is it this one?
U over Q.
Or is it different?
U over that is that's a potential energy. Okay, that's a potential. So this also equal to the potential energy code is this U, because U. Okay. Yeah. Sometimes they use U. That's right. In this case, it was U. So it's potential difference equal to QV. That's potential energy. Yeah. Okay. It's different.
Right, okay.
Different.
Okay.
So this is work. Yeah. This is work. This is the potential energy. Electrical potential energy. Electrical potential energy. So electrical
energy. Okay.
How many type of potential energy you have studied so far? Do you remember?
Gravitational potential energy.
This is one. That's one.
Yeah.
Anything else?
Chemical, elastic.
Elastic. The chemical is very abstract. Chemical potential is just the electrical potential. I can tell you. What.
Yeah.
So there's no chemical. There's no chemical energy.
Right.
Can you follow me?
It's just the.
It's electrostatic energy. This is gravity in a uniform. Right. Okay. This is potential energy for the spring. Okay. Elastic, that's x squared. And this is also, so this in electricity, we just use U to represent the potential energy, which is inconsistent, okay? But you just bear in mind that is the same type of energy, originally from different physical resources, okay?
Okay.
These are, I can tell you what, these are two basic formulas. So 1, 2, 3 are very useful. This is 3 and 4. Okay.
Okay.
Of course, to be exact, they must be equal to change in the potential energy.
Right. Change.
So basically, the connection between these two formula is connected by what we call the work done or equal to the change in the energy. That is what we call the work energy theorem. Okay.
Work energy theorem. Okay.
They have many forms. They have many forms. Okay. Anyway, I will stop here. I've just returned here and return everything here. In other words, if you use this formula, we just pick up one of formula to explain how to, if we just pick up this one formula here, okay. So in other words, the unit of W, so because of this formula, we can argue that the formula of W were equal to formula, sorry, not formula, the unit of W were equal to unit of the QV, okay?
Unit of QV.
Actually, you can actually do this individually. Can you just mathematics? That's called the dimension analysis. Have you studied dimensional analysis?
No.
Not yet. They just analyze the formula. For example, if you have derived a new formula, right? You are not sure whether it's right. Then you can do this analysis, okay? If the formula, if the units are the same on both sides, you can be sure the form is correct. Perhaps only error is just a coefficient. Okay.
Right. Okay.
Anyway, what is the unit? What is the unit for Q in international system?
coulombs?
Yes. What unit for voltage?
Voltage.
Volt.
Ohms.
Volt. Can you see?
Oh, volt.
C
Yeah,
volt.
sorry.
Okay.
That's resistance. Yeah.
In other words, what this also implies that this also equal to 1.6 multiply 10 to power next 19 CV. Do you agree?
CV.
In other words,
yeah.
see,
Right.
in other words, 1 joule will equal to 1 CV. Do you understand? Coulomb voltage.
Mm-hmm.
Okay.
Yeah, Coulomb voltage.
So in this case, so if you really want to do this translation, you have to understand what is electrical charge. Sorry, what is the charge of electron in the unit of Coulomb? You see,
So
the charge of electron is the unit, okay? It's element of the charge, okay? Do you know this formula?
Right.
Let just draw your attention. All the electrical charge, I can use a small q because it's all the electrical charge can be written as a multiple of the E. You know this formula?
No. All electric charge.
Oh, you have to learn
multiple.
because the electron is a particle, you see. You cannot divide the charge smaller than electron. Okay?
Right, okay.
Except that Cine standard model.
Right, yeah.
Okay. Electron charge, electron in the context of chemistry and ordinary physics, okay? And the charge of electron is minimum. It's just like an atom, okay? The charge of electron is
fundamental.
The fundamental unit, smallest.
Right.
Therefore, can we use mathematical notation? So n here is integer, can you see?
Mm-hmm.
Okay.
Yeah.
Do you know the notation in math?
Yeah. Yes. Yeah.
Okay. So that's, this formula is as important as the concept of atom.
Oh, wow.
Yeah. Why? Do you know why? Well, it takes 1,000 years before people to understand the mass can be written as a multiple of mass of atom.
Yes.
N is integer. See, these are two basic ideas in physics. Okay, I'm glad you have chance to know this now.
To learn this, yeah.
Yeah. Now, in the spatial case, that if you have studied electrochemistry? That's done by Faraday. So one Faraday were equal to Avogadro number multiplied E.
No, we haven't done that yet.
You have done that? Okay. Anyway. But of course, in chemistry, you have learned that. So one mole mass, monomass. So how about the monomass? 1 mole, the mass of 1 mole. How to write that? Mass of 1 mole, or you just use R or A. Monomass. It's called the mono. Have you seen monomass?
Yeah, monomass. Yeah. That's the measured in AMU, right?
Yeah, no, monomass is in gram. Be careful. What is monomass? Monomass will multiply this Avogadro number by the mass in U. See?
Right.
Confused?
Yeah.
That we do mass cancel A. Mass in U. Okay, this is A. I put all these things. So this is in U. Okay, in U. U is atomic mass unit. Okay. Anyway, we're not going to expand this knowledge here, but just remind you, these are all relevant knowledge. Okay. Now return to this question. You see, I can expand. You see, I can see one thing. I can expand into whole page. Anyway, return to this one. So if you check your formula sheet, you will see that the charge of electron, if you use the Coulomb, that is exactly equal to 1.6 multiplied 10 to the power -19. Got it now?
That's where it comes from. Okay, I see.
Do you understand these tricks now? Coulomb, like a gram. Coulomb, or another thing I tell every student is that how to convert 1 gram into what is the relation between 1 gram and 1 atomic unit? What is number shall I put it here?
Avogadro's.
Yes, that's right. You know that. I'm glad. And you know that. Yeah, you know that. Can you see that? So the gram is a huge unit for the mass of atom. okay?
Mm.
Similarly, the Coulomb is a huge charge relative to the charge of electron. Can you see that? So once you convert, once you rewrite this E here just represents a certain amount of charge, okay? Of course, once if this is convenient when we studied atomic physics, because do you remember that simple, do you know this formula now? Do you know what is this formula? You need to memorize this one. What is this formula? Energy.
N is equal to
N equal to 1, 2, 3. Do you know this formula?
No.
No. Oh, you should know. You should know. You should know. This is the total energy. The total energy. Sorry.
Total energy. Okay.
What? Give one more chance. Discrete. Discrete. What means it's discrete, not continue? Can you see this discrete? It's called discrete energy. Can you see? Total energy of what? When we will say discrete of.
Wasn't it with light, I think?
Hydrogen.
No. Oh, total energy of hydrogen.
Atom.
Oh, okay.
Okay.
Right. Okay.
Next time we'll focus on this one, and you can apply many basic knowledge here. You can use Newton's second law, and you can use the Coulomb's law. Okay, and you can also use the definition. Anyway, I will stop here because we'll return to your question. I haven't found any. I haven't answered anything about your question. All right, let's go to your question.
Interesting as well.
Interesting. Yeah. Okay,
I learned.
Okay.
Yeah. Okay. So
question: below two diagram, a diagram of left shows the energy level diagram of the unknown gas. Aha! Energy level. That is atom. Can you see? This energy level. Okay. So why we call it energy level? Because it's discrete. When you say the energy levels, which means that it's not continuous.
Right. Okay.
I can just reduce this one as this size is very small. Anyway, okay. So here we are. They have ionization. Can you see? This is unknown atom. It's not hydrogen. I can tell. It's not hydrogen. So it's. Can we just draw this diagram? How to draw this diagram? So basically, the vertical axis is not y, but energy now. Okay, that is energy level. That's called energy level. So in this case, obviously, energy can be written as is discrete. So this is energy. Can I put n here? And can you see all these negative numbers down there? Negative 2.7, negative 5.7, and the lowest is negative 8.2. So how to draw that? So we can. So in other words, all of this energy is less than or equal to 0. Do you agree?
Yeah.
What does that mean? What does that mean? Can we draw this diagram? Can we just indicate this is energy level? This is not the ground. This is actually the turning point when the electron inside atom become free. Okay.
Free ionization. Yeah. So that means you require that much energy to ionize.
Well, if the electron's energy, say, for example, if electron have go that far, so where can electron do you think electron will return to the to meet their mother or their parents? No, they escape. They're free. They grow up. They run away.
Yeah.
Okay.
Right.
So you can see. Can you just think of one? So they were run away. So basically, so this is a helium. It's a helium, right? Helium got two. I just draw simply. So they have two electrons here. It's helium. Okay.
Yeah.
And I just draw a symbolic orbit here. Just indicate that is a Bohr model. Okay, this Bohr model. Okay. So because of the attraction, electron inside atom are bound, are how to say restricted. Okay. Just like a kids. Okay. You are not allowed to go out. Okay. They are bound by their nuclear. Do you understand?
Right. Yeah.
So, however, therefore, their energy is always negative, because to fly, in order to fly outside, have you started? Do you remember photon electric effect?
Yeah.
Heard of that? In order to move outside with positive energy, you see, or you can say it's got a kinetic energy. Without that, they cannot move because their energy is negative. Can you see? So the kinetic energy is always positive. In other words, electron inside or near the inside atom are not free. Okay, they are bound. They are bound. They are chemically bound, but it's not chemically bound. Electrically attracted by the positive charge. You agree? So the force is always forcing them towards center, and in the meantime, they do circular motion. Okay, they can do circular motion.
Yeah.
Please, now return to the question. Yeah, that's Bohr model. Can we just finish this field diagram here? So basically, we have here several diagrams. I just slightly different color. So we got this atomic. First one is negative 2.7. This is not equal. Oh, okay. Something very interesting. Anyway, so we got these two ones. I think they have done it wrongly.
Wrong? Oh.
Yeah, I don't know why. Because almost they get more crowded toward this side. Okay.
They should be crowded at the top, right?
Yes.
Yeah.
Anyway, we just use this one. Oh, by the way, why did you mention ionization in this context? What does it mean, ionization?
Ionization.
Yeah.
The electron freeing itself from the orbit.
Yep. Electron become free. They cannot free themselves. Remember, you cannot accelerate yourself. Okay. Electron cannot free itself. They must absorb energy. Okay.
Right. Yeah.
The kids must be dependent on the parents if they don't have income. Do you understand?
Yeah.
You got income, you can buy the air ticket, you can fly. All right.
Right. Yeah.
Yes. The same thing. My kids were rebelling. My kids were sorry. That's simple physics.
Yeah.
Simple physics.
Yeah.
So basically, so that ionization is old, but traditional. It's bad. It's not good ideas. Okay. Ionization means something atom become ion. Okay, and electron become free. But basically, that if the electron can absorb some energy or do have some income, okay, they were first of all most of electron will stay in the bottom. Can you see? Okay, because that is this most stable. Okay, even for any reason, for example, during a chemical reaction, the electron may jump to somewhere due to confusion. Okay, but eventually they return to it's called the ground state. You know the ground state now? The ground state is the most stable. Just like this is a mountain. Can you see? This is a mountain hill. Can you see? So this guy here is most stable. It's dangerous here, unstable. Okay, so it's not unstable. So they all have a tendency to return to the bottom. Of course, the main reason is that they have attractive force acting on them. Just as we have the gravity downward all the time. Okay, so in this case, in the case of atom, it is a electrostatic force keep them in the innermost. This is called the innermost. Innermost. The ground state is called innermost orbit. Okay.
Innermost orbit. Okay.
Most orbit. You're not orbit. Shell. It's called you can call it shell.
Okay.
Anyway, so this question is talking about. So all of a sudden, some people something that is the main source is due to radiation. Okay, the photon will carry a certain amount of energy come here. Can you see? Do you know how much this is a photon? What is the formula for the energy of photon? Of course, they travel at the speed of light. But what is the energy of photon?
Energy of photon. What was it? F times the wavelength?
Oh, no.
Planck's constant times wavelength?
Right,
HF.
Yeah,
right.
HF, yes. Oh, this is very important. Okay. I read this one. This is very important formula. Okay. That is the beginning of quantum mechanics. Okay. So H is called Planck constant. Max Planck was the person who introduced this formula in 1900. You remember the history? I'd like to mention some history for students. Okay.
Okay. Yeah.
So that is a key formula for photon. Okay. This energy for the photon. So this is photon. When you see the photon, if you ask what's the energy of photon, that is a photon energy. Okay.
Right. Okay.
Of course, if you want, you can rewrite this formula if you know there's a C equal to lambda multiply F. Do you know this formula? Or velocity, wave velocity equal to the wavelength multiply the frequency. Do you know this formula? You're not familiar with. I hope you will eventually put all the useful formula on the single or 2 pages. All right.
2 pages. I think that's what I was. Yeah. Okay.
Okay. They are all basic formula here. Okay, they're both formula here. Now just I just write down here. I'm not good further, but if you combine these 2 formulas, I just stop there before I think after fit. Then you can rewrite this formula as C how to say C lambda or C velocity. C velocity. Hang on. H or H CH divided by lambda. So this is a derived formula. Okay. This is a derived formula. If you found these 2 formula together, if you combine this formula together. Now, let's return to the question. Now, the major experiment is to explain the absorption spectra. Okay, I just give you the. So this is absorption spectra. Okay, so in this case, you can have different. When you do the experiment, you will find some part is dark. Okay, I will here use just a straight line. So somewhere is missing. I just follow their notation. Okay, just follow their notation. Okay. So what happens here if you have the if you have the light source? This is how the experiment is done. The light source will generate white colors radiation, which means they contain all frequency, right? If you put your sample in these containers or tube, right? If you put the sample, it could be the gas, could be the liquid, okay? If you put your sample here, then you will get. Then after that, if you just use a prism, okay, you get observation or telescope, then you will see that these colors were divided into the different colors. Okay.
The spectrum. Yeah.
Let me see
spectrum,
how to draw. Yeah, the spectrum. Let's draw how. Let's kind of draw how to. I can just draw another one. I just want to. I don't want to redraw this again and again. Can we just just move backwards? So which is wavelength? This is 400, 500. This wavelength getting longer. Okay, understand now. So in this diagram, the wavelength getting longer. The wavelength getting longer. Okay, this wavelength. So if you just just prism here, and this is our sample. Okay, put our sample here. This is our light source. Okay, this is our light source.
Yeah.
Let's come here, and after that, after we receive this transmitted, this is a sample. This is your sample. Could it be the gas? Could it be liquid? This is your sample. Unknown. This is unknown gas. This is unknown sample. Could it be liquid? Could it be solid? Sorry, I spit 3 times. My kids remind me. I always repeat.
That's fine. It helps me remember it.
Okay. Anyway, so this prism. So basically, in this case, they were separated into different colors. Let's just say what is color. Oh yes, very close to the red one. I just use the red one. Yeah, it's not necessarily exact. Basically, you got. See, they were separated into different colors. Can you see? This is longest. This is longest. Can you see that? And probably get a green. Oops, sorry. Can you see that? It goes here. So this green, and probably the last one is purple. And the purple got the shortest. Okay, can you see that?
Yeah.
So you will see this just like a barcode in the supermarket. Okay. So this is called the absorption spectrum. Absorption spectrum. Today I just give you one introduction, and then you can do the analysis. So basically, during this interaction, the energy bring by the photon will be absorbed by electron. Okay, they have so many choice depending on the frequency. Okay, so they can go up. Okay. So for example, they can buy a ticket to the Sydney for the first attempt to escape the family, or if you get a large sum, they can go to Melbourne. Can you see? They can go to Melbourne. Okay.
Right.
Or if you got many, they can go overseas. Okay. Do you understand?
Right.
You understand?
Yeah, I understand.
So this amount of energy were determined by, can we just pick up one of them? Can we call this N2, this N1, okay? So basically the energy difference of electron, N2 minus N1 were equal to exactly the amount of this particular photon.
Oh, okay.
Do you understand? Okay.
So the E2 minus E1.
No, E2.
Can that's the. Yeah. I see. Because it jumped up that much, right?
Yeah. To be. Can we just call the final? Is called the initial. That's probably better. Okay. Can we call this final and initial? Okay. Because these are arbitrary. These are arbitrary. Okay. So this is what we call the resonance condition. Resonant absorption. Absorption condition. So it's actually energy conservation law. Do you agree? So this is a photon. This is photon energy. Photon's energy. Do you agree?
Yeah, yeah.
It is transferred. This transferred to the electron, so electron can go up. Okay, so that electron can go up. Can you see? Once they absorb this energy, can we just consider this example? This is the initial. They can jump.
Okay. Gets fully.
Yeah, they
fully
can
absorb.
Yeah, they can go to Sydney or Melbourne. Okay.
Yeah.
So once you got this one, another good way is a good example. In Australia, you cannot go everywhere. Okay, there are only several major cities, right? So if children disappear, so you can guess, well, either in Melbourne or Sydney. Okay.
Right. Yeah.
It couldn't be in between.
Not anywhere else.
Not in between. Okay, that's good. Okay. Anyway.
Yeah.
This is not your concern. That's my concern now. Okay. All right. Anyway. Now, this you can use this energy. You can use this formula to explain everything, but you have to do your own homework. Okay.
Okay.
Everything here is a principle. Okay, the principle. In other words, for example, if you just hypothetically consider, if you see this energy here, so this lambda, can we just say? Can we say this lambda 1? What is the number? I write down the number. 413. Okay, 413. Yeah, it's pretty. It should be around the. Can we call the number? Can we call the number is what is a 413 nanometers?
Yeah. Okay.
So this wavelength. Okay. So therefore, according to this derived formula, okay, you have to use the derived because the frequency can. So this formula, yeah, you do need this that derived formula. You have to use this derived formula, okay, to rewrite this one. That is a little bit challenging for you. So you have to rewrite this formula as E final minus E initial, okay, equal to HC divided by lambda. This is derived formula. See, this is another formula. Can you see? Same form. The formula can be written in different form. So after that, can you spend some time to work out by yourself how to use formula? In other words, in one word, one position in the spectrum is called the absorption spectrum. So this is called right down here. This whole thing is called absorption spectrum. It's called absorption atomical absorption spectrum. Okay, so it is called the 9. The 9-1, the 9-2. It's called each is called 9. Okay, this is called 9-3. Okay, each 9 will give you one wavelength. Okay, and the one wavelength you can determine the energy interval. Can you see?
Energy interval. Yeah.
So in other words, when you see the interval, you have to looking for this interval. Okay, to see which interval match which interval matches this exactly. Then you can say, haha, that is this guy go to Melbourne, this guy go to Sydney. Can you see? Do you understand?
Yeah. So you can use, I see.
Yeah.
Yeah.
So just remember
Okay.
this, just repeat. Each line in the atomic spectral absorption line will give you an interval. The interval is determined by 2 energy level. Okay.
Okay.
Then
Okay.
if you know this principle, you should be able to solve this problem.
Okay, yeah. I'll give it a try then. I'll
give it a try. We'll talk about next time. Okay.
Okay, yeah.
Okay, good. Do you want to save this or I will?
Yes, I saved it just now.
Yeah.
I saved the ones before.
Okay. You're going to already? Okay.
And if I want the lesson, I'll ask you.
Yeah, I will. Yeah, if you miss out something, I can send you the whole recording to you. All right.
Okay, yeah, that'll be good.
Okay.
I'll email you if I need it.
Okay. Goodbye.
Okay. Yeah. Thank you very much, Abdullah.
You're welcome.
I'll see you next time.
Okay.
Bye. Oh wait,
Bye.
wait a second.
Yeah.
Just quickly. Are we gonna have lessons over the holidays as well?
Well, better have, because for you, better have while working this.
Yeah.
I think it's important because you see,
That's
you have to keep the momentum toward the external exam. All right.
Yes.
There's no time to relax in the last holiday.
No, no, exactly. Yeah. Okay then.
Okay.
I'll see
See you next
week.
See you next.
Okay.
Goodbye.
Yeah. Bye.